Hello everyone, welcome back to my channel. Today we will solve the second problem of the jump game series. Let's look at the problem statement. An array of length n is given and the array is 0 indexed. That means the first index of the array is 0. Each element represents the maximum length of the forward jump that can be taken from index I. We have to find the minimum number of jumps required to reach the last index starting from index 0. We will try to utilize the approach described in the last jump game question. I have made a separate video for the same. Please watch that video first for better understanding and continuation of the problem solving approach. In this video, we will look how we can modify the previous approach and solve this problem statement. First, look at the naive or the brute force solution. Our approach for the brute force solution was recursion tree. In the given question, it assumed that we will reach the last index always. Let's draw the recursion tree again here with some modification and see how we can get the answer for this problem. So the given array is like this. Let's also write the indices. Now to draw the recursion tree, we have assumed the node structure will be like index and jump value to reach index I. So let's draw the recursion tree. Suppose we are at index 0. So the number of jumps required to reach index 0 is 0. Now the value at index 0 is 2. That means we will be having 2 branches. So we can reach index 1 with jump of value of 1, or we can go to index 2 with jump value of 1. Now index 1 is having value 3. That means from this node we will be having 3 branches. We can go to index 2 with jump value of 2, or we can go to index 3 with jump value of 2. Similarly, we can go to index 4 with jump value of 2. You can see this is our last index and we have reached the last index with 2 number of jumps. So we have already found the answer, but for the completion of the recursion tree, I will draw the complete tree. And again, we will come back to another solution, which is a BFS solution using Q, but I will describe that in some time. Let's first complete the recursion tree. Now so index 2 is having value 1. That means this node will have one branch. So if we can go to index 3 with jump value of 2. So what we are doing, we are incrementing jump value by 1 each time. Now index 2 is having value 1. So this node will have one branch. So we can go to index 3 with jump value of 3. Similarly, from here we can go to index 4 with jump value of 3. From here we have already reached the last index, so nothing to do here. And from here we can go to last index 4 with jump value of 3. So nothing to do with these two nodes because we have already reached the last index, which is index 4. Now still there is a chance to explore this node. So we can go to index 4 with the jump value of 4. Again, from here nothing to explore further because we have already reached the last index. Now if you see the minimum of these nodes, if you compare the minimum number of jumps required to last node, the minimum value is 2 jumps. And if you see here from 0th index we can go to this first index, and from first index we can go to this index. So we are following this path. Let me change the color for better understanding. So basically we are following this path. 0th index to 1 index, then 1 to 4 index. So this is the path that we are following. So with this approach, this recursion tree approach, this will take exponential time to complete. But so anyway, we will be having a better solution that we will be discussing in some time. But another approach here that we can use is the BFS. So that means we can use BFS here. How we can use? So we can use a queue data structure here, right? And if you see as and when we are first time we are encountering the last index 4, we will break out from the loop and we will give the answer, because when the first time I'm reaching index 4 with the jump value, that means we have already reached the last index and nothing, that will be the minimum number of jumps required. So if we do this thing, like use queue data structure, where each node, if we maintain the same structure like queue of a pair value, where each pair is basically the indices and the jump required to reach. If we do in that way, let's discuss this BFS thing, how that thing will work. So we will first insert this 0 comma 0 in the queue. That means, so q means so what that means, 0th index with 0 number of jumps. Next, we will remove this thing from queue, and 0th index is having value 2. That means we can go to index 1 with jump value of 1, and we can go to index 2 with jump value of 1. Then in the next run, we will pick this and we will remove this thing from the queue, this 1 comma 1, and that means from index 1 there are three possibilities. So we can go to 2, 3 and 4 index, but we can maintain one visited node array. And as you can see, we have already visited index 2, so we will not push anything for index 2 again, because as we have already visited index 2, that means we have found the minimum number of jumps required to reach index 2. Now we will be pushing index 3 with jump value of 2 and index 4 with jump value of 2. Here we are, as we are okay, let's continue the process and we will pop this thing from the queue. Now we will come to here. One thing we can do is like, as we are encountering the last index n minus 1 with jump value of 2, then we can come out of it and we can say like, okay, we have found, we can set a flag like we have found index, the last index with jump value of 2, and that we can return. So in this way we can continue the process. Or other thing is like, you can while picking up the next time, if you see like we have reached the last index, then we can remove that, we can pick the solution and we can return the number of jumps from the BFS. So for the BFS method, the time complexity will be order of n, because we are visiting each node at one time, and the space complexity will be order of n maximum, because it's like if any jump value is having maximum n number of jumps, if we can take from a node, then this is the solution, order of n. But space is also required, order of n. Now we can how we can further improve it. So we will be now we can improve in the time, we can have the time complexity order of n, but we can improve in the terms of space complexity. We can use constant space complexity. So now we will look for how we can use improved space complexity solution. Now we have seen the brute force solution, which is of time complexity of exponential time complexity. That is basically top-down approach to solve the problem. We have seen another method using DFS, which is using queue data structure. The time complexity is of order of n and space complexity is also order of n. Now we want to evolve the solution and we want to move towards an optimal solution. So we can further improve the brute force solution, which is the recursion tree method. And as you know, like dynamic programming is a better version or optimal version after recursion tree. So we will try to derive the DP solution from the brute force solution, where as the brute force solution was top-down approach, we will do a DP solution with bottom-up approach. And if you see, like we will try to derive the DP solution from the brute force solution. Still, we will be having order of n square, time complexity and space complexity is order of n. Then we will be having optimal solution, which is of linear time complexity, and space complexity is order of 1, which is constant. So these are the different methods or to solve the problem with different approaches and with different time and space complexity. But this is the general way how we can start from brute force and try different methods to solve a problem, and eventually we move towards the optimal solution. Now we will see the DP solution, which is bottom up approach, and next we will see the optimal solution. Now let's look at the optimal solution. So the given array is 2, 3, 1, 1, 4. Let's write the indices. Okay. Now, the optimal solution, we will follow the greedy method. Why greedy? Because for every index I, the maximum reaches I plus array of I. So, let's suppose this value is j. Now, if from I can reach maximum j, that means from in between all the points I'm able to reach from I, and as I'm trying to get the minimum number of jump, for every I will try to get the maximum reach, which will help me to reach the last index in a fast forward way. So let's assume let's see from index 0, my maximum reach is 0 plus 2, 2. So this is my maximum reach. And currently I was able till I was positioning at index 0. As my maximum reach is greater than my current position, so I'm supposed to take one jump. So I will have the jump value as 1, or increment jump value from 0 to 1. Next, this is my maximum reach, so I'm able to reach in between any point. So let's suppose with maximum reach index 2, I'm able to position at index 1. Now from 3, I'm able to have maximum reach till 4. So my maximum reach will get updated to 4 because of this greedy method. Still, with the previous jump, I'm able to reach till this point. So when I'm at index I equals to 1, my situation is I have taken one jump and I can reach till I equals to 2, and I have possibility to reach I equals to 4. then I will get incremented to 2. So my reach is now this reach is now equals to my current index. So I need to increment my jump one more time so that I can reach my reach becomes my maximum reach. So I will increment my jump value plus plus, which means my jump will be 2. And next my reach will be what? So I am at index 2. So my reach will be maximum reach, right? Because with previous I am able to reach this 4. My reach will be 4. And also my maximum reach is get 4. So when I am index 2, that means I have taken 2 jump, and with this jump I am able to reach till index 4, and also my maximum reach is 4. Then I will keep on incrementing. I will go to index 3. I'm able to explore index 3 because which is my under my current reach value. So jump will not get incremented. Reach will not get incremented. Also max reach is will it is a maximum. So we will continue on this part. And then anyway we have reached till n minus 1. So I will return. I will come out of my execution or exploring the indices, and I will return my jump. So my jump value will return 2. So in this case, if you see, we are not using any extra space. So the space complexity will be order of 1, and time complexity will be order of n. Now we'll look into the code. Now let's do the coding. So I'm taking the size of the given array. This is my current index I. My maximum reach currently it's 0. My reach is currently 0. Jump is also 0. Therefore, I will start with index 0 and I will be less than n minus 1 I plus plus. So my maximum reach will be always maximum of maximum reach, and I plus nums of I. If my current index is already reach, then I'm required to increment my jump, and also this will be my max reach. And as it is assumed that I'm also able to reach the last index of the array, so it's not required to check anything. I can return the jump. Let's see if it handles the base case also. This will handle the base case because base case will be nums of size is 1. If it is 1, then jump will be 0. Let's run this thing on the test cases. It is accepted. Let's submit this. The solution is accepted. Here, the time complexity is order of n and space complexity is order of 1. One thing here, like it is assumed that the we are always able to reach the last index, but if it happens like it's not always the case that we can reach the last index, how we can add the edge cases. Now to add the checks over here, we will add one flag here. For example, it's a bool flag which is false. Here I will check every time. If I is greater than reach, I will set the flag to true and I will break. Here, if flag is true, I will return -1. So, whenever my current index is greater than reach, that means I'm not able to reach the last index. Let's run this updated code. It's accepted. Let's submit it. This is also accepted. So with this small modification, we are able to add the test cases when it's the test cases where we are not able to reach the last index.